for the opportunity to present our recent theoretical work on unconventional superconductors. And in particular, I want to thank Claude Bourgonet for the chance to substitute for my advisor, Andrei Levin, who unfortunately could not present today. So the topic of this talk is the possibility of a triplet superconducting phase in a highly anisotropic layered compound, the lithium purple bronze. But I want to mention at the outset that the results that I will present will be quite general in the context of quasi-one-dimensional superconductors. Our work is motivated by several factors. First, the upper critical magnetic field is one of the most fundamental properties of the superconducting state. And the detailed orientation studies of Hc2 in quasi-1D compounds can reveal important information as to the nature of the parent symmetry in a given compound. And for the lithium purple bronze, the upper critical fields have been recently experimentally measured along all three crystallographic directions. Also, anisotropic compounds are known to be characterized by different exotic phases. Obviously, triplet pairing is important. It is believed to be in the perovskite strontium-ruthenate compound, and is actually firmly established in a heavy fermion compound, uranium-platinum-3. Also, the Markin-Ovchinnikov phase, which has been shown to exist in the organic TMTSF compound with a ClO4, and the reentrant superconducting phase. But just purely from the theoretical standpoint, triplet pairing is interesting because it's so unusual and rare. And one of the signs of its presence is extremely large values of the upper critical field. And of course, the earlier experiments on the quasi-1D organic compounds do show this trend of Hc2 exceeding the paramagnetic limit. So for the new candidate, the lithium purple bronze, what are some of the telltale signs that it might be spin triplet? Well, first, the upper critical field parallel to the conducting chains has been recently measured to be 15 Tesla, which is 5 times the paramagnetic limit. And a very distinctive feature of these measurements is that the paramagnetic limit has been experimentally extracted from this compound from the known polysusceptibility and the specific heat jump at Tc. So it's fairly well established and it does not depend on any theoretical model. Furthermore, it was shown experimentally that spin orbit scattering does not contribute much to the suppression of the paramagnetic limit because the purple bronze seems to be in a clean limit. This was done from measurements of the mean transport, mean free path measurements. However, there are several arguments against triplet pairing, and one of them is that for magnetic field applied parallel to the conducting chains, the orbital destructive effects are minimized due to very small interchain hopping. Other arguments would be a combination of many factors, such as in the organic TMTSF compounds and so on. So we intend to show, and our main result is that superconductivity can actually be destroyed by orbital effects, even for parallel fields, or fields parallel to the conducting chains, when this condition is satisfied, that the perpendicular coherence length is greater than the interplane separation of the layers. So that is our theoretical result. This plot has been extracted from a recent publication by Mercuri and collaborators, which shows the upper critical fields as a function of temperature for all directions. In particular, parallel to the chains, the black boxes here show a trend which seems to saturate at 15 Tesla here. And this dashed curve is just the best line that they have fit to their data. The perpendicular directions are also plotted here, and they're scaled. For example, the z direction of upper critical field is scaled by a factor of 12 here, showing a large anisotropy. And from this plot, we're able to calculate the Ginzburg-Landau slopes at Tc through linear interpolation, which will help us determine the relevant superconducting and band parameters for this compound. So for our general phenomenological description for quasi-Lambda systems, we start with the anisotropic electron spectrum. The Fermi surface here is represented by two slightly warped sheets extending in the z direction. And the p-wave symmetry that we assume for the order parameter changes its sign on the two quasi-one-dimensional sheets. The dispersion relation is linearized in this way on the two sheets with this constraint holding. The magnetic field is in plane and parallel to the conducting chains. The orbital part of the Hamiltonian is obtained through Peierls substitution, and in this case, the Schrödinger equation admits exact solutions for the wave functions. Having obtained the wave functions, we calculate the finite temperature Green's functions through a standard procedure. So in the case of the triplet superconducting order parameter, we take the simplest case where the order parameter changes its sign on the two sheets of the Fermi surface. I here is just a unit matrix in the spin space, and delta function of y includes the orbital destructive effects against superconductivity. The integral gap equation for delta of y, represented here, is obtained through the microscopic Garikov equations for unconventional superconductors. This pairing diagram leads to this rather complicated integral equation. However, there are several points I want to emphasize. First is that near the critical temperature, Tc, we can show that this integral equation for the order parameter reduces to the Ginzburg-Landau limit. From there, we can calculate the parameters such as the coherence lengths. This equation describes anisotropic 3D superconductivity in the appropriate limit, and also reproduces the results of the Lorentz-Doniak model in the opposite extreme, where electrons are confined to two dimensions. It also includes the description of the reentrant phase, summarized on a diagram from an earlier work by Levitt here. So our intent is to solve this integral equation numerically under the conditions where we can neglect the quantum effects resulting from the Bragg electron reflection. In this work by Levitt, it is shown that these effects can be neglected for temperatures higher than T star, which for the lithium purple bronze turns out to be only 60 millikelvin. And for low enough magnetic fields, which in this case are of the order of 300 Tesla, but the conditions under which the upper critical fields have been measured for the purple bronze are well within these limits. As far as the Lorentz-Doniak model is concerned, the requirement is that for the model to apply, the coherence length has to be smaller than the interplane separation of the layers. But in this compound, we show that the perpendicular coherence length is 20 angstroms, and it is bigger than the interplane separation, and therefore there is good coupling between the layers, and the quasi-1D picture, which holds for the normal state of this conductor, becomes 3D anisotropic superconducting phase below TC. In this case, it's possible to show that the integral equation for the superconducting gap reduces to this form here, which we can render to numerical analysis. So, near the TC, it's possible to show that the superconducting gap equation reproduces the familiar Ginzburg-Landau relations, and we can find the coherence lengths along all crystallographic directions. And from the measured values of the ratios of Hc2 at the critical temperature reported in the experimental paper that I quoted earlier, we can find all the superconducting and band parameters here. So there are two important numbers to notice. First is 20 angstroms is the perpendicular coherence length, which is greater than interplane separation, good coupling, anisotropic 3D superconductivity, and also the parallel coherence length of the order of 400 angstroms turns out to be much less than Boltzmann transport mean free path, which was measured for the superconductor, and it shows that this compound is in a clean limit. So spin orbit scattering does not contribute. This is a typical low temperature solution for delta of Y, which clearly shows unconventional behavior. Note the decaying oscillations as a function of distance in contrast to 3D isotropic superconductors, which usually decay as an exponential. In fact, the scale of these oscillations can be shown to be of the order of the parallel coherence length along the conductive chains. And finally, this is the temperature dependence of the upper critical field parallel to the conducting chains. The black boxes are the same as the ones reported in the experimental paper, simply overplotted here. The red curve is our theoretical calculation of the upper critical field, and we go down to about 60 millitesla. As you can see, it does show saturation about 15 Tesla, and there is excellent quantitative agreement between theory and experiment in this temperature range. So to summarize our results, is that we have shown theoretically that for quasi-1D system, superconductivity can be destroyed by pure orbital effects, even for fields parallel to the conducting chains. In the case of the lithium purple bronze, there are many signs in favor of triplet pairing, and it would, we believe it would take a difficult combination of factors in a singlet case to suppress the paramagnetic limit enough to be 5 times less, as was demonstrated in experiments, and also supported by the fact that there is excellent quantitative agreement in this temperature range. Thank you.
Okay, thank you very much. So, other questions? I can take maybe one question. I guess this is a more general question or a slight confusion. I see that the system you're describing is a quasi-one-dimensional system, but it seems like you're using a Fermi liquid behavior or something of a higher dimensional description to describe it, and it fits, but it's 1D and then a more higher dimensional system description instead. I guess I'm curious as to why you're doing that.
The Fermi liquid description is restored at low temperatures. The Latinger liquid description should emerge at much higher temperatures in this compound. In fact, around 30 Kelvin. But for low temperatures, this is essentially a 3D anisotropic superconductor. So the Fermi liquid description is restored at these low temperatures. And also, for this compound, we have measurements of magnetoresistance, which shows quadratic behavior at temperatures below 4 Kelvin. Quadratic in magnetic field, which is one of the tests of Fermi liquid fields. Does it answer the question?
Yes, thanks. Okay, let's thank the speaker once again. And we come to the next talk of the session, Kaizo Modata will give the talk from